the next topic, fuel cells. I will introduce next speaker. The next speaker is I²CNER Bishop. He is assistant professor of I²CNER in Kyushu University. He focused on the solid state materials for use in future energy sources. So let's start your lecture.
Thank you, Chairman, for the introduction. Yes, today I'm going to talk about some of the fuel cell activities going on in the fuel cell division here at Kyushu University. And this is both the solid oxide fuel cells, but also proton electrolyte fuel cells as well. And so basically, I²CNER, one of I²CNER's goals, or main goal, is to create a hydrogen economy, or create the materials and systems needed for the hydrogen economy. So this involves primarily producing hydrogen, storing hydrogen, distributing hydrogen, but ultimately consuming that hydrogen in a fuel cell in order to produce electricity. And so in the fuel cell division, we're working on developing these new next generation fuel cells, and with electrical efficiencies possible on the order of greater than 60%, and total efficiencies when you account for using waste heat of up to 90% have been suggested. And so in the fuel cell division, it's an international group of the 4 PIs here, where we have Professor Harry Tuller, who has worked a lot on electroceramics from Massachusetts Institute of Technology and related to fuel cells and sensors. Professor Kazunari Sasaki, who is here at Kyushu University, and he has worked a lot on building fuel cells, both solid oxide fuel cell and also polymer electrolyte fuel cells. And Professor Ludwig Gaukler from ETH Zurich, who's done a lot of work on ceramics processing and also micro solid oxide fuel cell fabrication. And then finally, Professor Nakashima, who is also at Kyushu University and has been working on working with new materials, new electrocatalysts for both room temperature, elevated temperature polymer electrolyte fuel cell operation. And so the objectives of the fuel cell division are to understand the fundamentals of solid-state electrochemistry, to establish or extend really the fuel cell science across both the polymer electrolyte fuel cells and the solid oxide fuel cells, and doing this with an eye towards the nanostructural levels. And so one of the roadblocks in fuel cell science is the limited operation range of electrolyte and electrode materials and durability issues that go along with this. So in a solid oxide fuel cell, we basically have limits on the amount of ionic conductivity we have through the electrolyte, and then particularly the overpotentials with the oxygen reduction reaction at the cathode. And these become very important as we reduce the temperature of the cell. And then in the PEFC, you have similar arguments where you have the ionic conductivity of the electrolyte as well for protons now, and also issues with the oxygen reduction reaction, which Professor Gaworth is going to elaborate much more in detail on that in the presentation after mine. So our approach is basically to work on elucidating these reaction transport mechanisms on the electronic, atomic, and molecular scale in fuel cells, and to develop new materials, electrocatalysts, electrolytes, and assemblies, and use new concepts to make these cells work better. And so here's a relatively busy slide of some of the specific topics in the fuel cell division. But I've broken it down more into 3 areas, which is the electrolyte areas where, for example, ionic resistance is a critical parameter, electrodes where we're increasing surface reaction rates, and then the overall cell and system where you have durability and versatility challenges, working with fuel flexibles, stress chemical relationships, phase-stable cells. And I'm going to point out a few examples in this presentation of work that we're doing here at Kyushu University on these challenges. So I'm going to start off with some of my own research in solid oxide fuel cell electrochemomechanics. And basically the first one I want to point out is the advanced characterization techniques, or more detailed characterization techniques used to extract key parameters of the gas-solid interface transport of these systems. So here, by going to a thin film morphology where we can control the geometry, we can pinpoint the reaction site as the surface of this particular oxide mixed conductor as the limiting reaction for oxygen incorporation. And then now we can change the morphology of that surface, or put different catalysts on the surface and analyze how we can target enhancing this rate of oxygen exchange at the surface. And also extract the key parameter, the surface exchange coefficient, which defines how easily this material oxygen comes in and out, and then use that to actually make predictive models of the defect concentration within these materials. So one thing that happens with solid oxide, or in these mixed ionic electronic conductors, as oxygen comes in and out, the material actually expands and contracts. And if we're changing the environment of the fuel cell, hydrogen to oxygen, or different temperatures, this can result in a gradient of defects within the material, which can result in a gradient of stress due to these expansion of the different defects. And so we've modeled that, and also looking to reduce this chemical expansion that occurs by first understanding the origin of it. A vacancy creates a contraction, but actually there's an expansion due to the change in the valence state of the ion. And then use this knowledge to actually try to reduce this chemical expansion in these materials. And other work going on in the proton electrolyte fuel cell area is led by Professor Nakashima, where he's been working on a high temperature PEFC material. This is starting with a carbon nanotube support, loading it with this PBI high temperature proton conducting material. This is to avoid water condensation, so operating above 100 degrees C, and then load it up with platinum and actually put it in a cell with the PBI membrane, as the catalyst here is the PBI, these tubes, and then operate it and show that actually he gets reasonable power densities at elevated temperatures, avoiding flooding issues. And then another example is Kazunari Sasaki's research on polymer electrolyte fuel cells, where he's looking at replacing carbon, which is known as, can have a carbon corrosion problem over time. You lose the carbon in the electrode, and it changes the morphology, and so your cell loses power over time, or the efficiency goes down. And so he's replaced some of the carbon with tin oxide, and then loading up the tin oxide nanoparticles now with very fine platinum particles all over the surface, and then shown through this cycles of kind of in a fuel cell operation that for one, the platinum loaded on vulcanized carbon, actually the electrochemical surface area related to the efficiency drops rapidly, but then the tin oxide support maintains relatively good efficiency over many, many cycles. And so now we also have some new inter-divisional collaborations in the fuel cell group. We're looking at developing these new electrode materials on the nanoscale between Professor Akari and Hayashi and Professor Matsumoto on hydrogen production. And then looking also at combining our research in the fuel cell division on cross-linked polymer electrolyte membranes, also with hydrogen division, actually modeling how these membranes work. Looking at hydrogen storage on decorated doped graphene. This is with Professor Leith and Professor Shao in hydrogen storage. Investigating proton conducting amorphous oxides for pre-combustion CO2 separation. So this is taking some of the expertise of Professor Fujikawa in making very thin membranes in the CO2 separation division, and some of our electrochemical knowledge in the fuel cell division, and trying to investigate proton conductivity for separation from CO2. And then lastly, this large demonstration of utilization of renewable energy project that actually Professor Akiba just discussed in a couple presentations ago. And so this is just some photos of Professor Kazunari Sasaki's lab within the fuel cell division. We, of course, have more facilities, but basically we have a large number of fuel cell test units, a microscopy lab with very good characterization tools, this durability test lab where we can do very long-term tests. Durability is one of the key issues in fuel cells. You don't just want to make a cell that works for 10 minutes. You want to make it last for many, many hours. And then also a fuel cell factory where we can actually create our own materials. So we don't have to buy off-the-shelf components or membranes, for instance, or oxide materials. We can fabricate whatever we want and then make it here. And this leverages funds available from other organizations, funding agencies in Japan, along with the MEX funding through the WPI. And so some of our proposed future work was to look at these carbon-free electrocatalysts, looking at nanostructuring our electrodes, as well as making very thin membranes and microfabrication. Alternatives to naphtha electrolytes, can we go to higher temperatures? Working with these polymer electrolyte fuel cells with tailored gas diffusion layers, so meeting some of the challenges of what do we do with water once we form it in PEFCs. Low temperature micro solid oxide fuel cells, basically again thin membranes, nanostructuring materials, impurity tolerant, so now we can work with available fuels that have impurities. We're not going to be limited to ultra pure hydrogen. And then monolithic cells for phase stability, and also again biogas, which is good fuel. So in summary, I just wanted to point out the uniqueness of the fuel cell division. So we're a truly international fuel cell research team, and we're interdisciplinary team, both high temperature and low temperature fuel cells. And we have open innovation for fuel cells, meaning that basically we have the facilities, and we're thinking of a variety of ideas of how to improve fuel cells within our international group. And so here's just a picture of most of the fuel cell team. There's actually some there that can be added now, and then in addition, some collaborations going on with the hydrogen production. And thank you much for your time.